Nuclear reactions, turning mass into energy. As we go through the following nuclear reactions, the decay process, the fission, and the fusion process, you have to keep one simple rule in mind. The mass of the product must always be less than the mass of the parent reactant. By having less mass on the right side of the equation than we have on the left side of the equation, this is going to allow energy to be released, and it's going to increase the binding energy per nucleon of the resulting product, whatever that product may be.
Okay, so let's take a look at some of the previous problems that we had looked at in topic 6.2, and that is the natural process, the natural decay process called the alpha decay. We could look at any one of the three processes, but particularly you would be responsible for understanding how the alpha decay works. And let's take as an example, let's just use the example from the book, and this is the decay of the particle radium. This is radium-226. Radium-226 has a Z number of 88, and when it undergoes the decay process, it undergoes the decay to become 222 radon, and this has an Z number of 86, plus it releases an alpha particle, sorry. This helium nucleus is the same thing, of course. Now this brings up an interesting sort of dilemma, and that is what I could do is determine the mass of the nucleus of radium, determine the mass of the nucleus of radon, and for this what I would choose is not the alpha particle, but instead, because the problem is I can't look the alpha particle up in a table, but what I can look up in the back of the table is the helium nucleus, or the helium atom I should say. And the helium atom is the same thing as the alpha particle, except that the helium atom also has the electrons. So this is the thing. Over here I've got 88 protons, therefore this atom would have 88 electrons. Over on this side I have radon, which has 86 protons, meaning that it also has 86 electrons. And if instead of considering this to be an alpha particle, I consider this to be a helium atom, then the helium atom would also have 2 electrons. So I have 2 plus 86, which is 88 electrons, and over here I have 88 electrons. So what this allows me to do is I don't need to worry about the electrons, because when I subtract the difference between their masses, the masses on the left and the mass on the right, the electrons are going to go away anyways. It's like saying that I have 5 on one side and 2 and 3 on the other. The 2 plus 3 over here is 5, the 5 on either side, that's a wash, and it doesn't have any effect on the calculation. So rather than calculate the mass of each nucleus, I can just look at the mass of the atom, and I know that the electrons will cancel out in the end. So when this particle undergoes its decay, radium, when it undergoes, and they give a nice diagram in the book, it decays into a slightly smaller radius atomic nuclei called radon and a very tiny little particle called helium, or the alpha particle. Now the alpha particle is going to go away with a very large velocity, and the radon is going to go away with a very small velocity, and this is because, of course, when the two particles break apart, they still have to follow the law of conservation of momentum. The total momentum has to be conserved, and if we assume that this particle was at rest in the beginning, then that means that the total momentum of the system has to remain 0. Now this guy with a very large atomic mass of 222, and this guy, the helium or the alpha particle, with a mass of only 4, obviously this guy is going to go away with a much larger velocity in the opposite direction from the radon particle. Now if you remember that the formula for kinetic energy is a little more complex. Kinetic energy is equal to 1/2 mv squared. So although these two guys will go away with the same amount of momentum, they don't go away with the same amount of energy. This guy is going to go away with much less energy, because it turns out that kinetic energy is more dependent on the velocity of the particle than it is on the mass. So as you can see, 222 to 4, that's approximately a 50 to 1 mass comparison. So that means that this guy will go away the helium particle will go away with 50 times more velocity to account for that conservation of momentum. With a 50 times increase in velocity, that has a much bigger impact on the kinetic energy than the mass. So the kinetic energy here is not conserved. In fact, this kinetic energy didn't exist before the decay. The energy was bound up. It was inside of the nucleus, and when the particles decayed, part of that energy that was inside the nucleus was spontaneously turned into kinetic energy as the two particles fired away from each other. So let's take a look at the actual masses of these particles, and let's see how much energy we actually get as a result of this decay process. So it turns out that the mass of radium is equal to 226.0254 U's, and the mass of radon is equal to 222, this is all from the table in the back of the book, 0176 U's. The mass of the helium is 4.0026 U. And if I add these two together to give me the combined mass of the two particles on the left, on the right I should say, then I end up with a total mass of 226.0202 U. Now, if we make a comparison between the mass of the two particles after the decay and the mass of the radium before the decay, you can see that the mass of the radium is slightly more, 0.025 compared to 0.020. So that turns out to produce a small amount of energy. Now, to see how much energy, I need to actually subtract. So 226.0254 minus 222.0202 gives me a very small mass defect of 0.0052. And remember, this is symbolized by the lowercase d, lowercase delta. So it turns out that we get approximately a mass defect of 0.0052 U's, 0.052 U's, in terms of MeVs, that turns out to be approximately 4.84 MeVs. Okay? Now that's the amount of energy that I get from one decay. But obviously, we would typically have a much larger number of decays. We would have thousands, millions, billions of these particles. So let's take a look at, let's assume that we had a very small sample, only 50 grams. And this is the example that they use in the book. If we had 50 grams of radium, the question is, how much energy is released by 50 grams of radium? Well, first of all, what we need to do is to figure out how many atoms of radium do we have in 50 grams, and that's simply a mole conversion. So we take 50.0 grams, and what I know, and I can actually tell this by looking back up here, there are 226 grams of radium for every 1 mole. 226 grams for 1 mole. And I know that for every 1 mole, there are 6.022 times 10 to the 23rd atoms. So, if I make that calculation, I would find that 50 grams of radium actually contains approximately 1.3 times 10 to the 23rd So I have approximately 1.3 times 10 to the 23rd radium atoms. This is a very large number of radium atoms. Now, if I take the number of radium atoms that I have and I multiply it by the amount of energy that I get from one radium atom, I'll get the total amount of energy that I release from the 50 grams. Now, this decay process, of course, is relatively slow. Radium takes pretty significantly long time to decay. So this is the total amount of energy that we'll get once the entire decay process has gone through and all of the radium have decayed into radon and to helium. So by multiplying these two numbers together to get my total energy, that's 4.84 MeV multiplied by 1.3 times 10 to the 23rd atoms, and I would end up with a total amount of energy of approximately 6.3 times 10 to the 23rd MeV. And as the book points out, we could go ahead and convert those. So 6.3 times 10 to the 23rd MeV. I know that in 1 MeV there are 10 to the 6th EVs, and I know that in 1 EV there is 1.6 times 10 to the minus 19th joules, and so this gives me a value of approximately, let's see, this gives me approximately 1.008 times 10 to the 11th joules. So a sample of 50 grams of radium will produce approximately 10 to the 11th joules of energy. 1 times 10 to the 11th joules is approximately the same amount of energy that's required to power a 100-watt light bulb for about 32 years. So although the individual atom gives off a relatively small amount of energy, although 4 mega electron volts is a pretty significant amount of energy, just a small sample of only 50 grams will produce enough energy over its lifetime to power a 100-watt light bulb for about almost a third of your life.